Hey, come friend. Not So start solving this problem. The coil, but explain one that I'll tell you. There is something called as clock roll. With a coil, clock roll. Clock roll. Clock rule. Now, do you know rule? Explain one about it. Yeah. You can also come friend. So look at this problem. Try solving this. So listen. So here the problem is a long straight wire carrying a current of 30 ampere is placed in an external uniform magnetic field of value 4 into 10 power minus 4 Tesla. So how is it placed? It is placed parallel to the current. Correction. It is placed in an external uniform magnetic field of 4 into 10 power minus 4 Tesla, and it has got generated parallel to the current flowing in the wire. Okay. Find the magnitude of the resultant magnetic field at a point 2 centimeter away from the wire. So basically, you have a long straight wire. Long is infinitely long. You have a straight wire which carries a current of I equal to 30 ampere. Now, this conductor, due to its own current, will produce magnetic field. But what is happening here is, in addition to the magnetic field that is produced by it, there is also an external magnetic field which is existing. And that magnetic field is existing parallel to the direction of current. And its magnitude is how much? So I'll call this as BEXT, which is external, right? And what is the value of it? It is going to be 4 into 10 power minus 4 Tesla. Here. So there is a point which is considered 2 centimeter away from this wire. At this point, our job is to find what is going to be the magnetic field. It is not the magnetic field due to the current carrying conductor. It is the resultant magnetic field. So we need to understand what they are actually asking. So if you observe, this conductor is placed like this, right? This conductor is placed like this. A minute. Those who are online.
Sir.
Yeah. Yeah. So just wondering if you people were there. Okay. Yeah. So listen. The first conductor is placed like this, and the magnetic field is parallel to it. It is like this, right? So if I take a point P on the right of this current carrying conductor, then what is going to be the direction of magnetic field? Using right hand thumb rule, we can conclude. So current is like this. Take the thumb and place it like this. It is going to be into the plane, right? Into the plane is going to be negative Z axis. So to put it simple, the external magnetic field is upward like this, and the other magnetic field is like this, right? So if you actually see it from the other side, they both are perpendicular to each other, right? They both are perpendicular to each other. So the resultant magnetic field that we are going to write, right? So the resultant magnetic field that we are going to write is going to be equal to root of B1 square plus B2 square plus 2 times B1 B2 cos theta. Basically, what I applied is parallelogram law of vectors. And remember, the value of theta between both the magnetic fields is pi by 2. Right? So here, what is going to be the value of B1 square? That is going to be 4 into 10 power minus 4, the whole square, plus what is going to be the value of B2 square? We have not yet calculated. That's what we need to calculate. Plus 2 times B1 B2 cos 90. Cos 90 is a 0. So the third value can be ignored. So it is only going to be root of 4 into 10 power minus 4 the whole square plus that something square. We'll calculate what that value is. So magnetic field at point P is going to be equal to mu naught I divided by 2 pi into A. Mu naught I divided by 2 pi into A. And we know that mu naught by 2 pi is going to be 2 into 10 power minus 7 into what is the value of I? It is going to be 30 ampere, the whole divided by, what is the distance? 2 centimeters. So it is 2 into 10 power minus 2. So 2 and 2 will get cancelled. You will get the answer as 3 into 10 power minus 4 Tesla. So basically you will get 30 into 10 power minus 5. So 30 into 10 power minus 5 is the same as 3 into 10 power minus 4. So the value that we are supposed to substitute here is 3 into 10 power minus 4, the whole square. So what is common in both? 10 power minus 4. So it will be square root of 4 square plus 3 square into 10 power minus 4, the whole square. So 10 power minus 4, the whole square's square root is 10 power minus 4 into root of 4 square plus 3 square is going to be 5. So answer will be 5 into 10 power minus 4 Tesla. In this problem, we cannot define the direction because they didn't mention anything in the question. They didn't tell in which direction the current is flowing. And without that information, you cannot find the magnitude. And the second information that is missing in the question to find the direction is they didn't mention anything about which side the point P is with respect to the conductor. Okay, so without that, you cannot find the direction. That is why the question is very clear. Find the magnitude of the resultant magnetic field. And our job is done. Okay, yes. Make a note of it. Generally, when they give it, when nothing is mentioned, the question it is center. If it is endpoint, they will mention it. Shall I proceed? Okay. So try this. Figure shows two current carrying wires 1 and 2. Figure shows two current carrying wires 1 and 2. Find the magnitudes and directions of the magnetic fields at points P, Q, and R. Find it. Answer. Okay, listen. Okay. The question says, figure shows two current carrying wires, 1 and 2. Current carrying wires 1 and 2. Find the magnitudes and directions of the magnetic fields at which point? At point P, Q, and R. So each point is going to have individual magnetic field associated with it, and we need to find the value of it. Okay. So let's see how to do. So first point is, if I take it at point P, right? When I take it at point P, then due to the first conductor, what is the direction of magnetic field at point P? So if I apply the right hand thumb rule, here if you see the current is upward. So place the thumb here and curl the fingers. So it is going and hitting the paper. It is going and hitting the paper on the right hand side. So here it is into the plane. On the left hand side, it will be out of the plane. Okay. So what I will do is, first, I will write B1. So for B1, it is going to be mu naught I divided by 2 pi A. So mu naught by 2 pi is going to be 2 into 10 power minus 7 into what is the value of I? It is 20 divided by what is the value of A? It is 10. So 10 into 10 power minus 2. Right. So this will cancel this 2 times. So 2 into 2 is 4 into 10 power minus 7 by 10 power minus 2 is going to be 10 power minus 5 Tesla. What I do is, I always first find the magnitude, then I find the direction. So for direction, I'll put an arrow mark on top of this. So what is going to be the direction? It is going to be out of the plane. By using the right hand thumb rule, we understood that it is going to be out of the plane at point P. Right. Now, if I take B2, right, magnetic field due to the second conductor at point P, then what is going to be the value? It will be mu naught, let me call it as I dash divided by 2 pi A dash. So mu naught by 2 pi is again 2 into 10 power minus 7 into what is the value of I dash? It is going to be 30, the whole divided by A dash. A dash is going to be 10 plus 10 plus 10. It is going to be 30 into 10 power minus 2, 30 and 30 will get cancelled. So it will be 2 into 10 power minus 5 Tesla, where it is going to be into the plane. Observe. So due to this conductor, the current is flowing in the downward direction. So place the thumb like this, curl the fingers. It is going and hitting into the plane. So into the plane completely on the left of it. So due to the first conductor at point P, it is going to be out of the plane, and due to the second conductor, it is going to be into the plane. Our objective is to find the magnitude and direction. So for finding the magnitude and direction, if I calculate the net value, I will use the principle of superposition, where I will write it as B1 vector plus B2 vector. So what is the value of B1 vector? It is going to be 4 into 10 power minus 5 plus the value of B2 vector, I will write it as minus 2 into 10 power minus 5, because outside I consider to be positive, inside I consider to be negative. So what is going to be the resultant value? It will be 2 into 10 power minus 5 Tesla. So the answer will be 2 into 10 power minus 5 Tesla. And how is it going to be? It is going to be out of the plane. So I took it like that. It's up to you. So outside I took it as positive, inward negative. Since I got the positive value indicates that it is out, because out is considered to be positive, no? The final value is positive. So it is out of the plane. Clear? Okay. So listen to this. if I take the point Q, so if I take it at point Q, the conductors are like this. They are parallel to each other. Here the current is 20. Here the current is 30. There is a point Q here, which is going to be 10. And here also it is going to be 10. On the left-hand side, it is 10. On the right-hand side also it is 10. So this is Q, this is P, and this point is R. Right. Now our job is to find the magnetic field at point Q. So at Q, what we will do is, if you observe magnetic field due to the first conductor, this is the first conductor and this is the second conductor. So magnetic field due to the first conductor is again going to be mu naught I divided by 2 pi A. So mu naught by 2 pi is 2 into 10 power minus 7 into the value of I is going to be 20. The whole divided by 10 into 10 power minus 2. This will cancel this twice. So answer will be 4 into 10 power minus 7 Tesla. But this time it is going to be into the plane. Yeah. 4 into 10 power minus 5 Tesla. But this time it is going to be into the plane. Right? So this is the direction of current. Here it is going and hitting the board. So it will be into the plane. It is into the plane. Similarly, if I take B2, B2 will be equal to mu naught times I dash divided by 2 pi times A dash. So this will be how much? 2 into 10 power minus 7 into what is the value of I dash? It is going to be 30, the whole divided by, what is the distance? This is also 10, not point Q, no. This is also 10. So 10 into 10 power minus 2. So this will cancel this 3 times. So 3 into 2, it will be 6 into 10 power minus 5 Tesla. And if you see the current is downward, so curl the fingers, it is again going and hitting the plane. It is into the plane. So the net magnetic field here is going to be, right, here put the vector symbol. Why I'm putting vector symbol is I mentioned the direction also. Okay. So the net value of magnetic field is going to be equal to B1 vector plus B2 vector. So how much is that value going to be? It will be minus 10 into 10 power minus 5 Tesla. Here I put the minus sign because it is into the plane. Either you can write the answer like this, or you write 10 into 10 power minus 5 Tesla and put an into mark here. So this is the magnitude, this is the direction. That's what they asked in the question. No? Find the magnitude and direction. So resultant magnetic field is into the plane. Right? Similarly, if I do for the point R, if I do it for point R, B1 is going to be equal to mu naught I divided by 2 pi A. This will be 2 into 10 power minus 7 into I value is 20, the whole divided by, what is the value of A? So 10 plus 10 plus 10, it is going to be 30. So 30 into 10 power minus 2. So 1 0 and 0 are gone here. So 2 into 2 is 4 divided by 3 into 10 power minus 5 Tesla. So what is going to be the direction? So due to this conductor, it is going to be into the plane. So into the plane on the complete right side. So it is going to be into. Right? So here you will put a vector symbol. Then what about B2? B2 will be mu naught I dash divided by 2 pi A dash. So mu naught by 2 pi is again going to be 2 into 10 power minus 7 into what is the value of I dash? That's going to be 30, the whole divided by 10 into 10 power minus 2. Because from here to this point, the distance is 10. So 10 into 10 power minus 2, 0 and 0 are gone. So you will have 6 into 10 power minus 5 Tesla. For this conductor, if you take the thumb, it is going to be into the plane on the left of it. So here it will be out of the plane. So out of the plane. Now this is also converted as vector. What is going to be the net magnetic field? Net magnetic field will be B1 vector plus B2 vector. So how much is that? It is, if I take the outward direction to be positive, 6 into 10 power minus 5 minus 4 into 10 power minus 5 by 3. It's 4 by 3, no? 4 by 3 into 10 power minus 5. So you will get 18 minus 4, which is going to be 14 by 3 into 10 power minus 5 Tesla. But since I got a positive value, I took outward to be positive. So the resultant magnetic field in this case is going to be outward. It is going to be out of the plane. Clear? So this is how you need to approach the problems where you have two parallel conductors. Okay, we'll be learning this concept in the future also about force between two parallel current carrying conductors. At that time, we'll use a similar logic to solve or derive the equations. At that point, it will help you. I hope it is clear, right? So I can make a note of it. Sure. Those are online, are you able to understand?
Yes, sir.
Okay.
Yes, sir.
Next page. You're done? Copy. So write down the detailed solution. Okay. So first, what I said is forget about the opposite thing. If I into the thing, the other side will be out of waiting. Yeah, so I'll solve each problem. So the fourth problem is two parallel wires P and Q are placed at a substitution of R is equal to 6 centimeters. P and Q are two wires with a completed resistance of 6 centimeters. And they carry the current of 5 ampere and 2 ampere in opposite directions. Okay. Find the point on the line PQ where the resultant magnetic field is. Okay. So we have seen similar kind of problem in the case of electric field. So the question is, whenever you are dealing with vector quantities, right? If you need to find a point where the vector quantity gets manipulated, thing is you need to have those values of equal magnitude and exactly opposite directions. The point here. So this is what is supposed to happen. They should be in the opposite directions as well. For that, what we will take into consideration is C. First point to be noted in this problem is whenever they give you an into mark and a dot, it doesn't mean that into and dot is belonging only to magnetic fields. That is the first point you need to register. It is just used to indicate direction. It can be for direction of any physical quantity. In this case, it is for current. In the sense, when they put an into mark and I1, they are trying to say that the current carrying conductor is carrying the current into the plane. And here it is out of the plane. Okay. So give me a pen. If I take this nib to be the direction of current, this one and here the tip to be the direction of current. Here it is into the plane, here it is out of the plane. This is how it is. When you're seeing from this side, you are able to see only the point. Whereas if you just go to the top and see, this is how they'll appear. Understood? So this is what is happening. They are like this. If you just tilt and see, this is how they are going to appear. Clear? So the logic is again simple. What did I tell you? For you to find the resultant magnetic field to be zero, you need the fields to be in opposite direction and they should be of the same magnitude. Now, due to this current carrying conductor, which is carrying the current into the plane, what is going to be the direction of magnetic field on the right of it, on the left of it? So here I am concerned only about I1. So for I1, it's saying that my thumb is supposed to go into the plane. So put the thumb into the plane and curl the fingers. It is going downward. Right? It is going downward. So if I take this to be the first conductor, magnetic field due to the first conductor is in the downward direction. Right? So when I say downward, completely on the right hand side, it is going to be the downward direction only. Completely on the right hand side. Meaning here if it is downward, here also it is downward only. Now what about the second conductor? See, remember, whenever I am using this right hand thumb rule, right, I will ensure that I find the direction where it is into the plane or it is downward. I'll only see where I'll not completely curl like this and see. I'll see what is happening when I do only half the curl. See, observe, in this case, what is happening is the current is outward. So when I do half the curl, I'm not even completely curling it. When I do half the curl, at this point, my fingers are going up. Meaning on the right of this conductor I2, the magnetic field is going to be in the upward direction. So here it is going to be in the upward direction. This clearly indicates that on the other side, it is going to be in the downward direction. So here also it is downward. Here also it is downward. The reason why I'm taking three places is because one I'm considering on the left of both the conductors. One I'm taking in between the conductors, and third I'm taking completely on the right of both the conductors. I hope it makes sense, right? Now, if you observe, B1, since on the right of P is going to be downward, on the left it is going to be in the upward. So from the diagram, it is very clear that if at all I want to have the points where the magnetic field can be zero, it can either happen completely on left of both the conductors or completely on right of both the conductors. In between, it is not possible because they are getting added up. Even if their magnitudes are same, since the directions are not opposite, there is no possibility of them getting cancelled. They only get added up. Am I clear with that? Now, for point where the net magnetic field is zero, what should be the condition? B1 should be equal to B2 and they should be in opposite directions. So what we will do is, let us assume that R is a point where the magnetic field is zero. The net magnetic field is zero. Okay. First thing to be noted is the distance between P and Q is given here. How much is that? 6 centimeters. That is R. This X is an unknown value. X is measured from where? It is measured from Q. So since B1 is equal to B2, what I'm going to do is I will write mu naught I1 divided by how much is the distance from the point P to R? It is going to be 2 pi into R plus X. So this is going to be the magnitude of field due to the first conductor. What about the second one? This will be equal to mu naught I2 divided by 2 pi into just X. So mu naught by 2 pi and mu naught by 2 pi will get cancelled. So to put it simple, I1 divided by distance, current divided by distance is equal to the second current divided by the second distance. So if this question comes in MCQ, you can use this as a shortcut. You need not sit and do all these things. Okay, so I1 by corresponding distance from that conductor to the point is equal to the value of I2 divided by the corresponding distance from that conductor to the point. Clear? So I1 is how much? 5. 5 divided by R is 6. So 6 plus X is equal to I2 is 2. 2 divided by X, which implies 5X is equal to 12 plus 2X. So 5X is equal to 12 plus 2X. Bring it this side. 3X is equal to 12. So X is equal to 4 centimeters. So you can report the answer saying that 4 centimeters from the second conductor or 10 centimeters from the first conductor, where on the right of them is a point where the magnetic field is 0. But I have B1 and B2 opposite on the left side of the conductors as well. Why should I not consider this and see? Shall we try and see? Suppose I take this point, so this is taken as PQR, I take this point to be S. And let me say that the distance from P to S is Y. Okay. So similar logic is what I'm going to apply. B1 is equal to B2. Right. So I'm going to say B1 is equal to B2 at which point? At the point S. So B1 is equal to B2 means mu naught I1 divided by 2 pi Y is equal to mu naught I2 divided by 2 pi into R plus Y. So mu naught by 2 pi is lost. Same logic again. Current divided by distance is equal to current by distance. So what is the value of I1? It is 5 divided by Y is equal to 2 divided by 6 plus Y. So cross multiplying this, what will you get? 30 plus 5Y is equal to 2Y. So 30 is equal to minus 3Y, which implies Y is equal to minus 10 centimeter. And this value is not possible because it is distance and distance can't be negative. So there is only one point where the net magnetic field can be 0. That is happening on the right hand side in this scenario. So what is the important takeaway from here? the important point to be taken from here, this question is, the point will be whenever the currents in both the conductors are in opposite direction. I repeat, whenever the currents in the conductors are in opposite direction, the point where the magnetic field will be 0 can either be completely on the left-hand side or right-hand side. But who is going to decide whether it is left-hand side or right-hand side is the magnitude of the current. So that point where the net magnetic field is 0 is going to be closer to the point with lesser magnitude of current. It will be closer to the point with lesser magnitude of current. This is an important point to be noted. The reason being, magnetic field is inversely proportional to distance. Magnetic field is inversely proportional to distance, meaning if it is closer to the one with greater magnitude, current is also high, numerator is high, and the denominator is less. So the value will become even more high. So what I'm trying to say is, if you take a point very much far from the one with lesser magnitude, it can never match with the one which is produced by the current with a higher magnitude. So always the point should be considered away from the one with greater magnitude or closer to the one with lesser magnitude. This is a very, very, very important point. Why I'm telling this is, if this question comes in MCQ, you need not sit and do all these things. All that you need to do is, you know which point you need to take. Take the one closer to the lesser magnitude. Just write I1 by distance is equal to I2 by distance. You'll get the answer in one step. All these things you need to do only for subjective part. Am I clear with this? So make a note of it. And an important point here. When will you use this logic? Only when when will this happen? Only when the currents are in the opposite direction. If the currents are in the same direction, then you will get the point in between. It will exactly be the reverse scenario. Is the point clear? Make a note of it. Efficiency is output power by input power into 100. %70 efficient. அது எதுவும் பண்ண முடியாது, சில்லி மிஸ்டேக். அது பிடிக்கலையோ புரியலையா? எஃபிஷியன்சி தான் அவுட்புட், நீ கொடுக்குற இன்புட்டுக்கு எவ்வளவு அவுட்புட் வருதுன்னு அர்த்தம். 30% is lost. 30% 70% தான் எஃபிஷியன்ட்ரா. எப்படி சொல்றது உனக்கு? இப்போ இது ஒரு பைப்புன்னு வச்சுக்கோ, ஒரு ஹோல் இருக்குன்னு வச்சுக்கோ, இந்த பக்கம் தண்ணி ஊத்துற, இந்த பக்கம் தண்ணி வெளில வருது இல்ல, லெட்ஸ் சே இந்த பக்கம் 1 லிட்டர் ஊத்துற, but this side you're getting only 70% of it. 700 ml தான் வெளில வருதுன்னு வச்சுக்கோ. அப்ப அது எவ்வளவு எஃபிஷியன்ட்? அதுதான் மீனிங். நீ கொடுக்குற இன்புட்டுக்கு எவ்வளவு அவுட்புட் வெளில வருதுன்னு பாரு. Output by input. It's a comparative study. Efficiency is output by input. And efficiency is measured mostly in percentage. So அதனால into 100 பண்ணுவாங்க. It's not a fractional value. ஒன்றும் இல்லை, இந்த ஃபேன் சுத்துது, மோட்டர் இருக்குள்ள. ஒரு சில ஃபேன்ல அந்த மோட்டர் வந்து வீக்கா இருக்கும். கரண்ட் போகுது, போற கரண்ட்னால எவ்வளவு எஃபிஷியன்டா இது வேலை செய்யுதுன்னு ரொம்ப காம்ப்ளிகேட் பண்ணு. எஃபிஷியன்சினா எவ்வளவு எஃபிஷியன்டா வேலை செய்யுதுன்னு அர்த்தம். அவ்வளவு மோஸ்ட்லி எதுக்குன்னா எலக்ட்ரிக்கல் எலிமெண்ட்ஸ் அதுக்கெல்லாம் கால்குலேட் பண்ணுவோம். புரியுதா? Guys, shall we proceed? So look at this one. This I will solve. Listen to this. Okay. So the question is, use Biot-Savart law to obtain an expression for the magnetic field at the center of a coil, which is bent in the form of a square of side 2A carrying current I. Okay. So basically here, whenever we speak about the current carrying conductors or coils, right, there is a language that is used. If you see, if I use the word conductor, for example, if you look at the problems that we are solving, we see problems based on magnetic field due to a state current carrying, you're using the word conductor. So whenever we use the word conductor, it means it's an open system. It's an open system in the sense the ends are not connected. Whereas if you take the conductor and join the ends, that will no more be called as a conductor. You will call it as a loop. So they'll mention the word current carrying loop. If there are n number of loops present in it, you call it as a coil. Okay. And one more confusion that arises is whenever we use coil, people start thinking only about circular coil. Not necessary. Coil can take any shape depending on what is the mold. See, for example, if I take a wire and wind it around this, right? If I wind it like this around this, if I take it out, I'm going to get a circular shape. So this, if I have a number of turns, it's called as a circular coil. Whereas I don't use this pen as a mold, rather I use this as a mold. When I do this, right, I take it out, I'm not going to get a circular shape, rather it will be something like a rectangle. Okay, I didn't do it perfectly, but I hope you're able to understand what I'm trying to convey. So it is going to be a rectangular shape. So still it is called as a coil only. In a similar context, what they are trying to tell in this problem is, there is a wire, right, which is bent in the form of a square. Though they use the word coil here, right, it is still a loop only. Okay. So if I observe, I have a square like this. And what is going to be the side of each square? It is 2A. And this square is made up of how many conductors? It is made up of 4 conductors. I take 4 straight current carrying conductors of finite length. I join them. I get this shape. Are you able to understand what I'm saying? This is one conductor, second, third, and a fourth. So if I take the current in this current in this coil to be in clockwise direction, our job is to find the value of magnetic field due to the whole system at which point? At the center of the square. Clear? Am I clear with this? Okay. Now, this is of finite length of how much value? 2A. And what is going to be the distance from here till here? If this distance is 2A, half of it is going to be A. I hope that point is registered. Okay. Now, one concept I would like to stress and explain is when we take a finite conductor XY and we take a point here which is at a distance A from the current carrying conductor. Let's say the current in this is I. We derived an expression for it whose value is mu naught I divided by 4 pi A into sine phi 1 plus sine phi 2. If you refer some books, right, you will have mu naught I divided by 4 pi A. Instead of sine phi 1 plus sine phi 2, you will have, let's say, cos theta 1 plus cos theta 2. Both are correct, provided you know what is phi 1 and phi 2 and what is theta 1 and theta 2. So the one that we derived is this thing, right? So when we did this derivation, what is the important concept that we need to keep in mind? This is phi 1 and this is phi 2. So if you take the phi 1 and phi 2 near the point where you're trying to calculate the magnetic field, then you will write in terms of sine. Whereas if the angles are taken closer to the current carrying conductor itself, then you will write it in terms of cos. It's very simple. Logic is very simple. What is the relation between theta 1 and phi 1? Theta 1 is equal to 90 minus phi 1, or phi 1 is equal to 90 minus theta 1. So phi 1 is equal to how much? 90 minus theta 1. Substitute it here. Sine of 90 minus theta 1 is cos theta 1. That is why I wrote this. Similarly, phi 2 is 90 minus theta 2. Substitute it here, you will get cos theta 2. So that is why both are right, provided you know which formula to apply at the right time. Okay. So we are still going to use this only. I told this because some books use this formula. At the time, you should not get confused. Okay. So that is why don't memorize it, understand and read. Clear with this? So what I'm going to do is apply the same logic here. Since I'm interested to calculate at point O, here how much is angle going to be? This is 45 degrees and this is also going to be 45 degrees. Right? So if I take this to be the first conductor, what is a magnetic field at point O? What is the magnetic field due to the first conductor? It is going to be mu naught into I divided by 4 pi into the perpendicular distance. What is the perpendicular distance from the conductor to the point? It is A. Sine of, how much should I write? 45 plus sine 45. So how much is answer going to be? It will be mu naught I divided by 4 pi A into sine 45 is 1 by root 2 plus another sine 45 is 1 by root 2. We get 2 by root 2, which is root 2 itself. So this is going to be the magnitude of the field. See, since they didn't mention the direction of this problem, just to have clarity, we will take the direction. I took the direction to be clockwise. No, so when I put a vector symbol on top of it, what is going to be the direction of magnetic field? It is going to be, take the thumb, curl the fingers. My fingers are going and hitting the board. So it is going to be into the plane. So it is into the plane. Am I clear? So this is the magnetic field due to the first conductor. Now can I say, since the current in the first conductor and third conductor in opposite direction, magnetic field due to the third conductor will be out of the plane. So this and this will get added to nullify. Am I right? The previous problem only I told you. If the currents are in opposite direction, in between them, the magnetic fields will be in the same direction. This is again another common mistake that happens. Just because the currents are in opposite direction, they will not even think, they'll put that as minus sign and cancel it. So they will say that the whole value is 0. No. I've seen these mistakes. Okay. So don't make that mistake. I'm saying due to the third conductor, again, if you apply the right hand thumb rule, it is going to be into the plane. So due to the first conductor also into the plane, second conductor also it is into the plane. What about the second conductor? Sorry, due to the first and third, it is into the plane. What about the second conductor? Keep it like this. Again, it is into the plane. Due to the fourth conductor, again it is into the plane. So all the magnetic fields due to each conductor which is making this coil is into the plane. So B1 will be equal to, the same will be the value for B2 vector, B3 vector and B4 vector. Right? So if I take the value, the magnitude to be B itself, B1, B2, B3, B4 as B itself, then what is going to be the net magnetic field? Net magnetic field will be 4 times B1. Or B1 or whatever it is, 4 times B1. So it will be 4 root 2 times mu naught I divided by 4 pi A. 4 and 4 are gone. Answer will be root 2 times mu naught I divided by 4 pi A. And in this scenario, if I write it as a vector, sorry, correction. Sorry. It will be root 2 mu naught I divided by pi A. If I write this in the vector form, according to this problem, it will be into the plane. Is that clear? So this is going to be the magnitude. That is what they asked. So I explain the direction only for understanding purpose. Is that clear? So in this problem, if it is asked in the exam, don't mention the direction because the direction of current is not mentioned. Clear? So you can make a note of this. Those who are online, I hope you're able to understand.
Yes, sir.
Yes, sir.
Okay. So this will be the last problem for the day. Make a note of it. Sorry. Maybe a circular coil is converted. It's only one circle. When I get returns, it will be handy for the but we come only for the response. Suppose the returns are just multiply the magnetic field with them. How does it? Just multiply with them. One term and the other term, they both are in series. So series that thing will get multiplied in times cycle. Effect 10 times. Clear? As I mentioned, this chapter is slightly lengthy. If you see, I'm solving more problems because if the base is set right, Next part of the chapter I can guide you fast. English only we answer that. Everything that I'm discussing now is actually going to appear as a concept in the book. And the parallel conductor பார்த்தீங்கல்ல அது அப்படியே ஒரு கான்செப்டா வரும். This one will come as a concept. So it will be easy for you. So as time progresses, now you're using right hand thumb rule. For coils, you need not use right hand thumb rule. You can directly tell. Looking at it, you can see which is north, which is south. I will increase the not increasing or the same thing. Okay. So this part, as I told you, this is going to be the last problem we face. There is one more problem. The same thing, except the fact that it is going to the form of the field of magnetic. What is the magnetic field of the same problem? Okay, very good. So after this is another important concept. This is what I do. Look at the area. Circular current do this. So it is basically a coil is on the principal loop is a coil to further. Coil is a loop with enter. Simple answer. This process. With the loop coil, one turn enters. Enters. Sorry, enters the loop is a coil. One turn in the coil is a loop. So, why are you using this word repeated? The problem is need to whether you should use the capital in word. As you saw, you will be doing that, but the problem comes in another another important concept. There is a lot of visualizations. This I'll be dealing with tomorrow, and we'll do some more work based on this structure. So, with this part, this thing, the first part of the chapter will be the fire. Then we'll get into the second part. Actually, this chapter is broken into 3 parts. So, first part is about the Biot-Savart law. Second part is about the reverse. Reverse in the sense here, what is happening is current carrying conductor is producing field. No. Second part is what will happen if you place a current carrying conductor in field. So, third part will be about the magnet. Third part will be about some devices like galvanometer and everything. That I'll explain. Sure. Simple now. See, the chapter is lengthy, but it's simple only. Okay. So I hope it's clear, no? Tell you. So I'll see you tomorrow with this topic. Okay, those who are online, we can wind up this. Okay. If you have any questions, you can ask, or else we can wind.
I have no doubt, sir.
Okay.
Thank you, sir.
Yeah.